And so something that we're going to be concerned about we're talking about initial value problem solutions is going to concern the existence and uniqueness of these solutions. So generally, what's going to happen is when we solve an nth order differential equation, ordinary differential equation, we'll obtain n candidate solutions. So let's just say that's U1, U2, down through UN, all functions of your independent variable, which I think we've been saying is x. And then that's kind of the family of solutions. And we'll write a general solution. That's u of x is equal to c1 u1 of x plus c2 u2 of x down through cn un of x. And when we have an initial value problem, we're going to want to be able to solve for those c's using those initial conditions. Going back to this example we looked at, we had a first order equation, so we had a one function family of solutions, c, c1, sort of using the same notation, e to the 3x, and so we solve for the c using our initial conditions. So we're solving for those c1 through cn using the initial conditions. Oops. But sometimes this can't be done. And so the theorem that we're going to learn is going to concern two ideas called existence and uniqueness. So the idea of existence is sort of, is there a solution to this problem? And the idea of uniqueness is there exactly one solution to this problem? And both of these things are important. Kind of think about this from an application side. A lot of you are engineers. So if there's some sort of physical problem you're asked to solve, you would want to know that it can be solved, but also that there's only one way to solve it. It wouldn't be helpful if you're talking about one solution and somebody else is talking about a different one. To kind of put this in terms of something that maybe is more concrete to you than a differential equation, here's an algebraic problem, x squared equal to r. And so you could solve it for x. You would say x is equal to the square root of r real quick. So let's say if r is equal to -5, you have x is equal to the square root of -5, and no real solution exists. Somebody asked you to find a real number that makes x squared equal -5 work, and you said no, there's no x that makes that work. If r is equal to +5, you have x is equal to the square root of +5. But then there are two solutions. x equal to square root 5 and x equal to minus square root 5. And remembering that that's possible will be important later. So there's also no unique solution. If you ask two different people to solve this problem, they could give you those two different answers and you wouldn't be on the same page. So those are the two important ideas for us when we talk about solutions to differential equations, and they've sort of been formalized in a theorem that is a little tricky, so don't worry about it, just kind of try to take it all in. And we're going to talk about some rectangle R. In the, I'm going to say the XY plane because it's easier for you all to think about XY planes. You wouldn't be very happy if I had an XU plane, but here Y is sort of what we've been calling U. And it's given by A less than or equal to X less than or equal to B, and C less than or equal to Y less than or equal to D. So you could draw that rectangle in the XY plane. And then for some initial point, x0, y0, inside R, and f, a function of x and y, such that f and df dy are continuous over R, then there exists some interval I0 around that initial point, some distance h away from it, and inside the initial rectangle we were thinking about, and there's also going to be a unique function y of x over that interval. And it's going to satisfy the initial value problem given by dy dx is equal to that f of xy and y of x0 equal to y0. That's the whole theorem. And we'll kind of make that make more sense with an example in a little bit. First, what I'll do is kind of draw a picture for us. But just to kind of go back through this now that you've seen everything it says, what we're saying when we look at this theorem is that if you have some initial value problem, you know that you'll have a unique solution and it'll live in some special place as long as you can check that when you take the partial derivative of the right-hand side of your first order differential equation, the derivative of whatever your derivative is with respect to your dependent variable, if you can verify that that's continuous over that special interval, then you know that you have that unique solution. All of this, like rectangle R, A less than or equal to X less than or equal to B, C less than or equal to Y less than or equal to D, is sort of just bookkeeping for the theorem to make sense. What's really going to be important for you is going to be, let me undo all those marks and just make maybe one mark. What's going to be important for you is that df dy, that initial condition, and that interval near your initial condition where df dy is continuous. You'll get to see that a little bit later. I'm just going to draw a picture for those of us who think a little bit better this way. So a representation of the theorem would be the following. Here's our y, here's our x, here's A, B, C, and D. So this is the little rectangle where we live. There's x0, there's y0 at that point. And then here's our solution, y of x, right there, that lives between, actually, let's open parentheses, x0 minus h and x0 plus h. And so, for example, you might have like, well, we'll do the example in the next video. So that's just a picture of the rectangle, and here is our interval I, over which our solution, y of x, that's unique to the initial value problem exists. So click on through for an example and then a wrap-up that tells you the practice problem for this week.